Glad to be here, and thank you everyone for coming here to the session. My name is Hamid Akhtar, and I am currently with Percona as the Technical Product Manager for Postgres. So I'm going to discuss today how to evaluate different tools, what kind of tools there are available that can be utilized for query performance insights, and what kind of value they deliver. So a bit more about myself. More than 20 years of professional software development experience. Started working at a very early age with programming back in '93 in 7th, 8th grade. Currently part of Percona, and I've just been enjoying some amazing culture at Percona. So prior to that, I was with Enterprise DB for 8 years, managing the configuration department. And some of the key things that we did there were Postgres official installers, the one-click Linux, OS X, Windows, all those installers, and occasionally working with Devrim on the RPM packaging side of things. So in case you need to connect, here's my email address, my Skype handle, and the WhatsApp code that you can scan just to get in touch with me. So some initial thoughts. The presentation will just kind of set the stage at the very start. We'll discuss how the planner yeah. So how the planner behaves, how it develops a plan. We'll also look at some of the tools that are available. I've picked up some of the most commonly used ones, and then at the end there is a Percona product that we're developing, PGStat Monitor. So the tools are selected for various different purposes. They offer different value from end user perspective. So we're going to look at what they provide and some of the deficiencies or challenges when we start using them. So initial thoughts, let's I guess it's important that we understand how we would like to evaluate query performance. When I look at query performance, I think it's important that we look at it from a holistic perspective, from the application side onto the eventual execution. So not just what's happening in Postgres, but also the ability to track back to the application so that you can identify what application issued that query from which host. And also, again, it's important to know at what time that query was executed. Query text, some of the challenges that you'll see with query text or some of the tool extensions that are out there is that they do not provide you with actual parameter values. So they provide you with placeholders. And those placeholders then become a challenge because you then have to go and figure out yourself what values were there. And that, in a huge table, can be a challenge because values can, different values will output different number of rows, whether it's a single row output for a particular value or whether it's going to return 10,000 rows, and that's going to really identify the behavior of that query. We're going to obviously then once from application to query text, then the next point is the execution plan, and that is what defines how the query will be executed, what kind of different steps the server Postgres will take in completing that query processing job. Once that's done, you'd like to know the planning and execution time statistics. So how much time was taken in planning, how much time was actually taken in execution, the kind of I/O or the operations for blocks were, so statistics on those are also important to understand because you might be fetching the same amount of data, but where you're fetching it from, whether it's from cache or whether it's from disk, that's also a key consideration when we are evaluating the performance. Finally, it's about events and locks. Is the query waiting on something? Is something blocking the operation? Is somebody just holding a lock that's preventing the query to do something? I think that's also a key consideration. So let's start with the very basic. I'm sure most of you are already familiar with this, but we'll just run through this. Explain and analyze. So allow me to explain, and we'll just proceed on with the analysis then. The query processing is actually broken down into 5 steps. It starts with the parser, followed by analyzer and rewriter. Parser and analyzer are really concerned with ensuring that the query is written properly. There are no issues with the query. The rewriter then performs certain transformations on the query tree. So you'll end up with kind of a refined query tree that is then passed on to the planner. The planner will then, based on certain rules, statistics, internally maintained, will then generate a query plan, which will be passed on to the executor, which will then just execute those steps individually, whether sequentially or in parallel, depends on the configuration. So the thing that I'm going to focus on is planner and how the executor then works on it. So to understand how the planner does, what the planner does, what kind of things that it looks into, we'd have to understand the explain command output. At a very basic level, this is the simplest of an explain command output. What you see is that a SQL command is prepended with the explain keyword, and it prints out a plan. It has not executed the actual query. It is just presenting us what it thinks about the query and how it should be executed. So it's expecting that sequential scan will be done on this relation, and the cost of that, the setup cost, the startup cost is 0, and then you have the total cost of 445, and the number of rows is 10,000, and width is 244. To explain these values a little more, startup cost is any initial steps that might be required. So for example, if there's a sort operation, you can't just emit the rows out. You have to do sorting before you can start sharing those rows out. So if you're doing a sequential scan, you can simply access those rows and start emitting them if there are no other operations involved. Total cost is the time that it will take to complete the sequential scan. Not the time, sorry, we'll come to what the costs are actually. So it'll take, that's the estimated effort, rather, for completing the sequential scan for the entire tank 1 relation. The total number of rows, and this is coming from the statistics that Postgres is maintaining internally, and those are just a representation of the data. Those aren't actual number of rows, but those are the expected based on analysis, which may or may not be accurate at this time. Width is the average number of bytes that will be returned for each row. So 10,000 rows, 244 bytes, you can multiply the two and get roughly the amount of data that will be returned. So the cost is actually an arbitrary number. It has no real world association, except for that it's basically defined as the effort required to do a sequential page access, and that's conventionally defined, or by default defined as 1.0. So it's a relative number. Basically, it's a proportion. So you can configure this according to your environment, your infrastructure, your hardware, and you can tune this. Then you have page costs, sequential and random. These are obviously going to be different in the sense that sequential scanning means that you can read on a continuous operation, and you can read sequentially the data. But random is where you would have to seek and go back and forth in the data files to access that piece of data. So there's different kind of costs that will be incurred. By default, sequential scan is set as the cost for it is set as 1. For random access, it's set at 4. However, that was for more the mechanical disks. The other disks will have different cost factors, and you can tune both of these and set different values to these to give them priority over the CPU cost that I'm going to then discuss. This is actually, the CPU cost is basically the time, the amount of effort that we're expecting to process a row, a tuple. And there are different types of then tuples, for example, whether that's from a relation, from an index, or whether there is, we need to perform certain operation on that row, whether we need to perform a filter operation. I think the default values are 0.01 for the tuple. It's half for the index one for that, and further it's half then for the operator. So index is 0.005, and the operator is 0.00025. So it's in that sequence. Finally, there are parallel costs with parallel workers. If you want to have a job that utilizes more than one worker thread, then there are setup costs for parallel workers because there will be an overhead for setting up those parallel workers. And then there is a cost when you have to share a tuple across parallel processes. So these are basic estimates of effort that the planner will look at in terms of evaluating how a SQL query should be executed. And based on these costs, it's going to make certain decisions whether an index will be used, whether a sequential scan will be used. So this is really the basis. A more complex plan with a few joins, a few filter statements, a few other things in here. And you can see, so a plan is, there are certain rows, for example, like bitmap index scan, and you have index scans. Those are basically how you'll get the data from the tables or the indexes. So those nodes indicate that there will be an access here of actual table or index, and which is going to either hit the cache or the disk. But there are other important keywords here. For example, the bitmap index scan. Earlier on, I mentioned that there is a random access and sequential access. With index, data is generally not stored sequentially because it might not be over a period of time. The data might get mixed up. Might get mixed up. So it might not be ordered in a particular way that you're trying to access. And hence, when you're scanning an index, the data is considered in random sequence. So what it does is, very smartly, it wants to reduce the access of actual files or pages. And that's where the bitmap keyword comes in. So what it's trying to do is, while it's scanning the index, it's actually creating a bitmap of pages that needs to be accessed. And then, based on that bitmap, you have a smaller set of pages that you should otherwise access. Because when you're scanning an index for each tuple or each entry in that index, you would want to go and read that tuple. So it's broken down into 2 steps, actually. The first is the index scan, and then it's scanning the heap. So the bitmap comes in from the index scan. It's ordered. It's in a way more from that random access. It's kind of transformed into sequential, a little bit of sequential access. Hence, it's more optimized then for access. And the bitmap heap scan will actually then scan those pages in a sorted way to make it less random and a little more sequential. You have a materialized keyword, so it will try to cache some of the data that is accessed through index scan, and it will just not to reread it multiple times if that's the case. You have loops, which will come in joins, and that's where you'll generally see the materialized node as well in a query plan, because the inner relation or the inner table might need to be iterated multiple times, and hence the materialization comes in. So just to recap, node plan is a tree of planned nodes. Nodes at the bottom level of the tree are scan nodes. So you can have sequential index or bitmap index scans. You can have non-table scans as well, whether they're functions like generate series that return a list, or you can have values. So you'll see those. Then I think just following up on the explain, there is another kind of addition to this command of explain analyze. What this actually does is it actually executes the command that, that was given to it. So explain was did not execute the command, and it was more about utilizing the statistics that are maintained within Postgres about that relation or those relations that are part of that query. This actually goes on and executes that plan. Why is this important? Because it allows us to correlate the costs that were there, that the planner was estimating, with actual time values. So you can see, for example, that the cost and the time. So setup cost was 0, but there was actually some time spent there. Then there was total time, and you can see that execution time was 18 milliseconds, and you can do a comparative analysis of the queries and tune your GUCs accordingly for the costings. So there is the additional value that analyze command presents here is the startup and total times in milliseconds, total rows returned, which may or may not be different. It also presents planning time, but you can also see that if you use the summary keyword with explain command, and then you have the execution time as well. So as I said, it's a way of explain analyze as a way of correlating the arbitrary cost numbers with the actual times, and that's a kind of a way of tuning those cost parameters better. So next, I think now that we've kind of discussed some of the basics of the plan and what kind of value we can get out of those plans, we need to look at some of the tools that are available out there. And in this talk, I'm going to discuss tools that are generally commonly available or used, and that are open source as well. They're used for different purpose, and we're just going to go through and how they fit into the entire scheme of things. Start with pgstat activity, followed by pgstat statements, auto-explain, pgBadger, and pgstat monitor. So pgstat activity is available. You don't have to do anything in Postgres. The moment you have your Postgres set up and running, you can query this view. It's a part of the catalog setup schema. So activity, as you can guess, it's really telling us what's happening currently with the within the Postgres server. What are the backends or the clients that are connected with it? What are they up to at this point in time? But the pieces of information that are useful in analyzing query is about connection and database and user. So the ability to track back to an application, because the performance is not just about how the server behaves, but it's also about the entire chain that you want to understand and then evaluate the performance in that context. So it tells you about the host IP, port, application, and backend type. So for some of these parameters, you'd have to enable certain GUCs. So host names might not be available by default in your setup. and they're not evaluated, but you'd have to enable that to capture the host names. Further on, it has timestamps for transactions and connections. So you can evaluate aging transactions. Why is that important? Aging transactions can have a detrimental effect on the system performance. They might be holding locks. They might be just holding back X-mens. And they might be just not doing anything useful, which means that the vacuum process might not be able to clean up. And even, say, any would cause additional bloat, would eventually could also cause you running out of transaction IDs as well. So it also maintains state. So for example, whether your connection is currently idle or whether it's doing something, idle is defined as in multiple types, like idle in transaction aborted. So you can actually see what that process is doing and whether it's idle or whether it's actually trying to do something, whether it's waiting on certain events, and that's an additional piece of information, whether it's waiting on certain locks. So it tells you really about what those backends are doing and what they're executing. You can also see those queries. So connection and application details. What could be of interest is anything that's idle in transaction. And even idle in transaction aborted could be of interest if you have save points in that transaction that were already executed, which means that they might be holding back other queries, and anything that's doing that over a much longer period of time will cause issues eventually, whether, say, they're holding any exclusive locks that are preventing other SQL queries to wait on them. In terms of time thresholds, you might want to have specific. You want to evaluate when the last state was changed for that particular connection, and you might want to have your own threshold, time threshold for that, for your particular use case. So based on that, you can see whether that's an expected behavior, that the state hasn't changed for a while, whether it's minutes, hours. And you can flag those through either some cron job or other mechanisms. Obviously, aging transactions, I've already gone through that. They're pretty useful. Wait events, if they're not null, then the backend or the connection is waiting on something. It might be active. So the state is different, and wait events are different. They're not joint in that sense. So it might, a connection might be active, but it might also be waiting on something during its process. The caveat unfortunately, with pgstat activity is that it will only tell you about the connections that are available right now, the clients that are connected right now. So what happened 5 minutes ago, if a client came in and connected after 5 minutes, you would not have that piece of information if you're trying to observe just this view. So the information really is ephemeral, and that's one of the challenges, that you have to monitor this on a continuous basis, whether you're monitoring it by saving that data. But that's one of the challenges with pgstat activity. pgstat statements is an extension that's available in the contrib module with Postgres. Needs to be installed separately. It's packaged with the contrib packages, whether RPM or debs. So it's a statistic focused extension. So it's going to provide you with a lot of numbers, with a lot of details. And what it really focuses on is planning and execution statistics. And it's not database specific, so it works for all databases once it's installed. And I use that term very specifically, installed. So the moment you have it as part of the installation directory and as part of preload shared libraries. It's going to work whether you've created the SQL extension or not. It's going to be active, and it's going to have that detrimental effect on the performance because it's part of now the execution path of the server. So it's going to inject hooks, it's going to have its callbacks, and it's going to have about 3 to 4% of performance degradation the moment you have it as part of shared preload libraries. Why it's needed as part of preload shared libraries? Because it's going to hold some memory. So it's going to acquire or take some shared memory. With PG14, there was one major change that came in, and that was compute query ID. Prior to that, the tools had to calculate those query IDs themselves, but now that need has been eliminated, which means that quite a bit of code changes were made to pgstat statements. And now it's relying on that compute query ID GUC that's by default on with the server. If it's off, then pgstat statements would not be able to capture any statistics. So you won't see any data if this is off. It has 33 columns in PG14. I think PG13 had 32 columns. The only change here was a top-level Boolean to indicate whether this query was a top-level query. By default, track planning is off because that will also have a further degradation, performance degradation for pgstat statements. And with this off, you'll see that all the planning columns, plan timings, they're going to be off. So you're going to see zeros for all of those. What it really provides is statistics. So total, min, max, mean, and standard deviation. Now that's pretty useful. Looking at it from outside, you have the min, max, mean. That's a lot of information, a lot of things that you can then kind of help stitch together and identify how a particular query is behaving. You have planning times, you have query execution times. You also have shared local temp disk blocks and statistics on those. The difference here is, so shared blocks are really your table and index access pages. Locals are basically, again, indexes and your temporary tables, and temp are basically the work mem or the operations that are needed to be done by to process a query. So whether, for example, sorting and data to be written for those things. So it tracks that, which is useful. And what it also tracks is how many times you've hit those. So whether they've been accessed from cache, or whether how many times have those been dirtied, and how many times those blocks have been written. You can get pretty similar information from explain analyze buffers, which will tell you about the number of times those blocks were hit. There's also other pieces of information that explain analyze buffers will give you for other operations like sort and stuff. And finally, it provides you information about wall statistics, like records and full page images and bytes. It does have a new view. I think this was one of the deficiencies in the older versions of pgstat statements, where you had no clue how long those statistics were being collected. So, for example, if you have total execution time of a particular query, you don't know whether that's over a period of day, 2 days, or 10 days. So there was no information in that sense when those statistics were last reset. With PG14, this additional view now provides that information. Also, pgstat statements is configured to hold a specific number of queries. I think the default is 5,000. With additional queries coming in, it deallocates some of the least used or least executed SQL queries. So this view, which is a single row view, now tells you how many times that deallocation has done, so that you know whether you need to configure that parameter better or change its value. So here's one use case, and this is taken from the documentation of PGStat statements, where you can, for a particular query, you can take and just select a couple of columns with calls and total execution times, rows being returned, and hit ratio. Hit ratio in the documentation and here is being defined as how many times you're getting that page or data from cache rather than accessing it from disk. It's a simple ratio of blocks hit and blocks hit plus read. Yeah, and then obviously you can sort it to see which queries are being executed more, which have the total time of the highest order. So that's a very useful way of looking at queries where the time is actually being spent in the execution. These are the challenges that I see with PGStat statements, actually, and there are quite a few. When looking at query performance, you also need to factor in at what time of day this was happening, whether this was after 12 a.m., whether this was 2 p.m., whether this was a time when the load was expected, and whether this was happening during when there was really no load on the server. And there's no information that PGStat statements can provide in that context. All it does is provide aggregated statistics from the last time that the reset command was issued for statistics. It provides you with planning details, but it does not, the execution time for planning, the average time for planning, the minimum time, the maximum time, and the standard deviation for planning time. But what it does not provide you with is the actual plan. So while you're looking at it, it's like not giving you the complete picture with regards to the plan that was generated. The other challenge is that it provides you with query text, but it does not provide you with relations or views that are impacted by queries. Would you then parse the query yourself? Because you would also want to look at from that perspective, not just from the perspective of query IDs, but you'd want to see which relations are the ones to look at and optimize, whether there has to be a deep loading of some of those views or of those relations. It does not provide you with actual SQL, the value of those parameters. So if you have a where clause, say x is equal to 5, it would just replace that with a parameter. So you'll see $1 or $1 followed by a number, but you would not have an actual value, which means that it then becomes a challenge of looking into or understanding what value was provided. And it then takes you away from PGStat statements because you'd have to go to another tool or another place, whether that's the application, whether those are the log files. But you'd have to move away from stat statements because the information here is not complete in that context. Finally, I think the biggest problem that I have with PGStat statements is that it does not provide you how well spread that data is. It's providing you with min-max values and standard deviation and average values. But what I would have liked to see was a histogram here to see how spread out that data is and kind of the buckets that they fall into. So just to emphasize that point a little further, so here are two tables, and if you look at the last row for each table, you'll see that the standard deviation is identical for both. The min-max values are identical. The only some variance, which obviously will not be exposed by PGStat statements, but mean is different. But mean does not give you an indication of how the performance was for over a period of time for that query. And if you look at the numbers in the first column, you'll see that the first table has 4 major anomalies. It has a query that took 1 millisecond. The same query took 1,000 milliseconds twice and 3,000. And it has also a 189, which I had to kind of tweak just to make sure to get the same standard deviation. But other than that, it has a 40, 50, and 60. But if you look at the second table, then it has 3 anomalies, and the scale of that anomaly is much less, because you have 3,000 and 500 rather than having 1,000, 1,000, and 3,000. So that's one of the challenges when I say that PGStat statement does not actually give an accurate picture of the spread of that data, because that is really the key to understanding whether there was a checkpoint happening at a particular time that was causing that 3,000 anomaly. And min, max, mean, and standard deviation, with that piece of information, you can't really track back to the detailed performance data. Next is auto-explain. It's a very small extension. It's a NoSQL extension, and it's useful in the sense of dumping the actual query plan. It has a lot of configuration parameters for the size of this extension, but that's generally to control how the explain command output details will be dumped into the log file. So you can also you set log min duration, which kind of defines the threshold after which any query taking more than that will have its plan dumped into the log files. Why this is beneficial? At times, an application might be doing certain operations that might seem innocuous, but they're going to change the behavior of the query. And from personal experience, I've seen that picking up that query from that application and dumping it into PSQL, I was getting an index scan, and that application was actually having a sequential scan. And in terms of the order of timings of those queries from application and the same query from within PSQL, it was more than 100 times performance difference. And this is where this extension comes in pretty handy in terms of dumping the actual query plan for you without having to do it manually. And it kind of hooks up within the planner and gets you the actual query plan or the explain analyze output. So so the challenge with this is that it's a NoSQL extension. So you'd have some kind of a log analyzer or some way to parse the log to be able to access this from the common interface of SQL. So you can't really see the plan yourself. And you'd have to go again outside the auto-explain environment or the SQL environment to get hold of this information. It's a very useful extension. It's part of the counter modules of Postgres, but unfortunately that NoSQL limitation was kind of a little challenging for me. pgBadger is a log analyzer. Why this is included? It's not really in the same kind of league as a counter module or an extension. It's a tool that resides outside. It's a Perl-based tool, which is very easy and simple to use. It's a very quick, fast log parser and analyzer, and it generates reports at the end, and those reports are very useful, actually. You need to make sure that you have configured your Postgres for dumping the required information that you're looking for in the log files, whether those are related to temp files that are being generated, because temp files will translate into you then tuning the work mem, because and what this tool does really well is it presents you with a nice, simple user interface, whether if you are generating an HTML output, and it has very simple UI, which with the menu on top, drop-down menus, and you can select the top queries that are, say, holding locks, the top queries that are being run frequently, the top queries that are taking most time, the query that had to wait most for a particular lock. So it provides all those information, and they present actual queries with simple graphs as well. You can output this report or generate this report in multiple formats, which means that you can have your own tools on top of it to consume that piece of information, whether it's dumped as JSON, then you can have your own tools that can then parse that, that information that has been captured by pgBadger. You don't want to overcook log file and dump everything into it while just testing out or running a couple of tests. I managed to generate a 4 GB log file running pgBench and make install check world in 15 minutes. So you can imagine what the server can do, and this was on a laptop with just over 5,000 TPS. So it picks up some of the statistics from the statistics table. A lot of this information gets dumped as part of log files if you have the required parameters set up. It provides way more information or in way simpler format than you could access from the statistic table. Postgres has more than 50 tables or views for statistics, whether those are stats for index, IOs, and stuff. But there are more than 50, and for you to go out and inspect those and stitch up a story out of those views and relations is going to be challenging. This tool can do that very simply from log files. This is an example, and you can see that atop the drop-down menus with multiple options, with checkpoints, with sessions, with connections, logs, queries, and top and events. So very useful, very simple to use. You can simply download this from the GitHub and start using it. I think it probably, for a couple of features, it does require some additional Perl tools, but otherwise it runs pretty simple and smoothly. Parsing huge files could be a challenge, but it does allow you to run that job in parallel. So you can use -j and parse the number of threads that you want to use for it, number of cores that you want to actually use for it. You'd have to set up a cron job to run this regularly, to analyze log files. Another good feature, perhaps, is that if you have log rotation on and you're generating reports on a daily basis, then it can incrementally use those log files and also generate a weekly report at the end summarizing what happened. The challenge with the interface is that it's not responsive, which means that it's not optimized for viewing on a smaller screen. So if you want to see this on your cell phone or a screen with less space, then the UI does not reorient itself. pgstat monitor is an extension by Percona. It's built specifically to capture the deficiencies that we've seen with some of the other tools like pgstat statements, pgstat activity, and auto-explain. So we've tried to combine all of these three tools together and provide one single user interface where you can have access to the plan, you can have access to the connection or session information, you can have the statistics, and those statistics are presented in a very different way. And all of this is available through a single SQL view, which has a lot of details in it. What's different in pgstat monitor is that it's designed differently. It's not designed to be aggregated as a single row per query. It's actually a time-based one. So you can define your time buckets. By default, it comes with the default configuration of 1-minute time buckets, and there are 10 of those. You can expand that, but it obviously requires more memory. We've tried to keep it very simple for the initial setup process. So it's going to maintain statistics per minute, and any query that ends in that bucket will be maintained in that. The data is very similar to the statistics data is very similar to pgstat statements, but additionally you have, the way we're grouping this is based on database, user, client, application name, query ID, and plan ID if plan capturing is enabled. So any plan changes will differentiate it as a separate row. What we do have is we have a huge number of more columns than pgstat statements, which provides you with the state information, provides you with the connection information, you also have the option of having comments in there, which in your SQL query, which will be captured separately. It also captures the parameters and top query ID so that you don't have to do kind of a hierarchical query yourself, but you have that, the ability to track back simply from that row and link back to the old query, and you also have the query text for it. So not just that query, but if it's being executed, say, through a nested query, then you have the access to that as well. It also provides you with a list of relations and views. That's very useful. That's one of the deficiencies that I saw with pgstat statements. Query meta information, where you can, if you've stored that as multi-line comments, it's going to capture that and maintain those key value pairs, which can be useful in tracking any information, any metadata about the application. So you can track whether this is coming from application X or Y, so that information can be maintained separately. And it stores actual parameter values. It does maintain placeholders, but it also provides you with the actual parameter values, which are extremely useful if you want to debug this. The buckets are recycled, so they're kind of in a circular queue. So the moment you go back to that bucket again, it will be reset and reutilized. So we're not excessively utilizing a lot of memory here. It also provides you with a histogram of query time. So you can see, for example, that the particular query in that particular time bucket executed two times from 0 to 3 milliseconds, or it executed once between 10 to 31 milliseconds. And that's very useful because you want to understand a pattern of how that query is behaving. This right now is in state of an RC. It's going to be GA this month. So that's where it stands. But you can, I would suggest and recommend you to try your hand at it and just look at, you can use our Percona distribution for it, which is not vendor locked in any way. It's also provided as part of the RPM packages from the PGDG setup, Yum repositories. So just to summarize what we've kind of captured, some of the use cases are that, for example, application connection information, the extensions that you can use or the tools that you can use for it, the stat activity and stat monitor, query text, stat statements, pgBadger, and pgstat monitor, and I should really have had pgstat activity here as well. Execution plan is auto explain, stat statements, Badger, and stat monitor. Planning and execution timing statistics, you can see it from stat statements, Badger, and monitor. Query execution timing histogram, that's stat monitor only. Blocks read or written, stat statements, Badger, and monitor. Wait events and logs, stat activity, and Badger. And SQL interface, that's stat activity, statements, and monitor. So you can see that stat monitor occurs very frequently. In the end, just at Percona, we want to make sure that you are free, you keep your freedom, so you have the choice to move around. Everything that we do is open source. There's no vendor locking in any way. And we're hiring with an amazing company culture at Percona. And if you want to discuss something, I'd love to talk to you about Postgres. We can sit down, have a cup of coffee, and discuss and talk Postgres. Thank you so much. And any questions that you may have.
Just a question on I know there's a parameter that's like log temp files, something like that. Do you recommend that in general to use as information for query analysis?
I think you should probably, logging should be kind of a second stage. You should really first look at, for example, stat statements and see whether there is a need to log, and if there's an excessive increase in the temp files that are being accessed, then you might want to do that, because it's going to impact the query performance, because that means that, say, a sort operation is now going to write files on disks, and which will make it slower, and you'll have to tune your work mem whether that means increasing that work mem or adding hardware resources. But it is very important in those operations then.
All right, and I think we are out of time, so thank you very much.
Thank you.